Linda is bored and decides to pour an entire container of salt into a pile on the kitchen floor. She pours 3 cubic inches of salt per second into a conical pile. So there I'm going to pause to draw our picture here. We have a conical pile, and the word conical tells us that the shape we're looking at is a cone. And so the cone's defining characteristics are the height h, and we've got the radius r. Okay. She pours 3 cubic inches of salt per second. So this 3 cubic inches per second needs some notation with it. And the units that we have, inches cubed per second, actually give us some sort of clue as to what the notation is that we have. So we see that it's a rate of change there over time. So since seconds is measured in time, we see that dt is on the bottom. And inches cubed would be a measurement of volume. So we're looking at dV dt is equal to 3 inches cubed per second. And that is a positive value because we're adding salt to this conical pile, meaning the volume is getting bigger, hence the positive value 3 for it. So let's keep going now. So this conical pile, it says, whose height is always 2/3 of its radius. So there's a relationship there. Height is equals 2/3 of is multiply of the radius r. So we have h is equal to 2/3 times r. And that's always the relationship at all periods of time. So it says when the radius of the salt pile is 2 inches, so it gives a fixed value r equals 2 inches. How fast are the radius and the height changing? So it's asking about dr dt and dh dt. We don't know what dr dt is. We don't know what dh dt is. We could think through what the units would be, but we need to know the value. So the units, we have inches cubed per second for dV dt, so we'd have per second in each case here. But volume is measured in cubic inches, tells us that the length measurements of the radius and the height would be inches. So we have the units already figured out. We also should note that each one of these is going to be positive because both the radius and the height are getting bigger as we add more salt. So the one other thing I want to mention here is this r equals 2 inches is a given fixed value, but that does not mean that r is constant. And that's really important here. Both r and h are changing with respect to time, so we cannot plug in that r equals 2 until after we take the derivative. But of course, derivative of what? We need an equation to work with. So the volume equation is our starting equation. We have volume equals 1/3 pi r squared h would be the volume of this cone. And as we have it stated here, we have 3 variables with respect to time. Volume's changing, radius is changing, height is changing. And so if we were to take the derivative right now, we'd have to use the product rule on the right-hand side. But actually with the extra piece of information that h is equal to 2/3 r, we could eliminate the h on the right-hand side so that we can avoid the product rule. And so that would be what I would advise. So we have volume equals 1/3 pi r squared, and in place of h, we're going to substitute the 2/3 r. And we can go ahead and clean that up to volume equals, we've got everything on the right-hand side is just terms multiplied together, so we can do it in whatever order we want. So I would see 1/3 times 2/3 would be 2/9. We've got a pi sitting there, and we've got r squared times r. And since we've got multiplication there with the same base, we add the exponents. So that would be to the 3rd power. So the equation that we need to take the derivative of is v equals 2/9 pi r cubed. So there we have it. V equals 2/9 pi r cubed, and we're ready to take the derivative. So ddt of v is equal to ddt of 2/9 pi r cubed. The left-hand derivative is simply the dv dt. The right-hand derivative is a constant multiple of 2/9 out front, with the pi also, 2/9 pi out front, all of that's a constant. And then we take the derivative of r cubed. So that's a power rule, but remember the r changes with respect to time, so we'd have to finish the derivative with the chain rule. So we bring down the power 3, drop the power on r by 1 to give us a new power of 2, and we finish off the chain rule by taking the derivative of the inside base there. So that would be dr dt. So let's go ahead and clean this up a little bit by just multiplying the numbers together. So we've got dv dt equals, we've got 2/9 pi times 3. So the 9 and the 3 have a common factor, so we can reduce that right away. And that would be then the 2 on the top, we've got a 3 on the bottom because we reduced out a factor of 3. Pi r squared dr dt. So taking a look at what we have in this step, we've been given values for dv dt and r, and dr dt is one of the two things we wanted to find. And so we can go ahead and plug in the value 3 that we know is dv dt, and we can plug in the value 2, which we know is r. And so then we can solve this for the only variable that we have, the only unknown that we have, dr dt. So we've got 3 equals, we've got 2/3 times pi times the 2 squared, which would be 4. So that pi and the 4 are understood to be like over 1. They live in the top of the fraction. So we're really looking at the top being 2 times pi times 4. So that would be 8 pi on the top with the 3 on the bottom, and we have dr dt. So as we're trying to solve for dr dt, typically we would think, well, we'll just divide out by what's in front. And that's true. But what's in front is a fraction, and so the equivalent thing would be multiplying both sides by the reciprocal of that fraction. And so that's what I would end up doing. So we would have the 3 times the reciprocal. The reciprocal of the fraction would be 3 over 8 pi. I just flip it. And then that would be equal to the dr dt. So flipping the equal sign around, we have dr dt is equal to 3 times 3 is 9 over 8 pi. Notice it is a positive value, and we already discussed that the unit should be inches per second. So we have one of the two things that we wanted to find out. And the last thing we want to find out is the dh dt. And to get dh dt, we could essentially just start over and work through the entire step again. Or we could be smart about it and realize that that relationship, h equals 2/3 r, always holds. And it in particular holds when r is equal to 2. And so what we could do is take that equation that relates h and r, and we can take the derivative of each side of that equation. So ddt of h is equal to ddt of 2/3 r. So on the left-hand side, we have dh dt is equal to, and we have the constant multiple 2/3, and then the derivative of r would be dr dt. Okay. And dr dt we worked pretty hard to get, but we found it. It's that 9 over 8 pi, so we can plug that in, and we have dh dt is equal to 2/3 times 9 over 8 pi. And we can multiply this out and reduce. We've got the 2 on the top that has a common factor with the 8 on the bottom. We have a 3 on the bottom that has a common factor with the 9 on the top. So what we get when we reduce is dh dt is equal to, we canceled out a 3 from the 9, leaving us with a factor of 3. And we canceled out a 2 from the 8, leaving us with a factor of 4 on the bottom. And then we've got the pi on the bottom also. Notice again, this is a positive value, as we expected, and the units are inches per second, as we already discussed.